All right, I just started recording. Yixing, I just started recording. Okay. So, hi everyone. So I think this is the last class of this semester, right? Happy to be here to give the last lecture on foundation models for code and math. So I guess first question of every lecture is asking the question of why. Why do we want this? So before answering that question, I want to do a quick poll. So how many of you have used or actively using GitHub Copilot while writing code? Okay, a lot of you. And how many of you that have used ChatGPT to ask code-related questions? All right, so I guess you don't need a lot of motivation in the section. So if you do, how to automatically write programs is one of the oldest and the hardest problems in AI and CS. So they started all the back to Alan Turing, which for which he said this process of constructing instruction tables, which means programming, maybe one day it gets dull, we can ask the machine to do it by itself. And also research around automatic program synthesis happens way before the era of large language models. And also they relate to several important areas in computer science. A lot of people and researchers from different domains try to tackle this problem, from program languages, software engineering, machine learning, natural language processing, and HCI. And also coding and doing math are great test bed for intelligence. And what we really want to measure for LLMs is also the level of intelligence. So by doing coding and math, we can measure the language understanding, symbolic reasoning, planning, search, and interact with learning abilities of those models. Just think about the thinking process and how complex it is for you to write a code or do math. Wouldn't it be cool if we have a model can also do that? And also, they definitely empower many real-world applications, such as maybe some of you use this flash fill. You define two columns, and the model will figure out the expression by itself. Virtual assistants like Siri, like Google Assistant that we're using these days, Alexa, and also AI-assisted programming like the GitHub Copilot I mentioned. Nowadays, it also includes robotic control. You can generate code to control robotic arm. And also for database queries and visualization for business intelligence purposes, you can also use a model to generate code so that it empowers people that doesn't know how to write code to query such databases and do such visualizations. So those are the motivation part. So before we start, here are some preliminaries. So in this lecture, I would assume basic knowledge on terms in NLP and related to large language models, such as you should know what BERT is, what GPT is, what's prompting, what does it mean to be autoregressive, and what's retrieval. And also, I'm going to be slightly abused and mixing some of the terms here. So in this lecture, foundation models approximately equals language models, approximately equals large language models. And because whether a model is a larger model or not is quite subjective, and also as time is related to the era it's in. So I'm going to be using those terms interchangeably. And also here I refer to a model as code LM as long as you have seen some code during training, regardless of its purpose or of its actual ability to write code. And yeah, this lecture is about code and math LLMs. They are code and math are deeply connected, as both they are formal languages, which differs from natural language. They are constrained by strict grammar, and both require symbolic reasoning to complete. So in this lecture, I will mostly focus on code language models, but most of the code language models also have some math reasoning ability, and many methods apply for math language model as well. And this is the outline of today's lecture. So first, I will give a brief history of code and math language models, and then I will talk about methods before training LLM, data collection, filtering, and tokenization. And then I'm going to talk about the several classes of how to train code language models and several methods how to improve code language models after training. So you can interrupt me at any time if you have questions. If I don't see your hand, just yell. Any questions so far? All right. So first, brief history lesson. So this really happened. Language model happened since birth, and the first bird for code happened in February 2020, where when CodeBird is out, and it's around 16 months after original bird paper. It's a pretty small model of 125 million parameters. And in the same year, GPT-3 paper is released. And in the training of GPT-3, code is not specifically used as a part of the training data. But when people play with it in the then OpenAI playground, people find that GPT-3 has some coding abilities. It can help you figure out some HTMLs, figure out some JavaScripts, mostly because it's trained on web data. And on the internet, there's also a lot of coding tutorials. So it's not surprising that I have some coding ability. So let me see if I can get rid of this. The blocking. Okay. So in June 2021, which I think is a very exciting moment, GitHub Copilot is released. So if you haven't been using something alike before, I think you will be amazed by its revolutionary performance. And before GitHub Copilot, multi-line whole function completion is not possible, basically. And also, people are using models restricted to single line completion. If the model can figure out where my brackets are, it'd be great. But ever since then, people are thinking about much bigger problems, and because the models are getting much more capable. So in a month, Codex paper is released. So this is really the hero behind the GitHub Copilot. It's a GPT-3 family model trained on code, and it's the first 10 billion plus model trained specifically for code by OpenAI. And many of the practices from that Codex paper is still used till today, including the PASA-K method that they used. And entering last year, in February last year, DeepMind released a paper named AlphaCode. This paper is now in Nature or Science. So it claims around 54% ranking in competitions with human participants in coding competitions, and it's up to 41 billion parameters. Though unfortunately, this model is not released or publicly accessible anywhere. And in another month, the open source world is catching up. So the CodeGen model is released, and it's the first open source 10 billion plus code language model. And later, we found that this model is severely undertrained. I believe in one of the lectures, Armin talked about Chinchilla, how to train a compute optimal language model. And later they took a lesson from that and trained CodeGen 2. And in another month, Palm paper it's out. This is the attempt from Google in the domain of large language models that results in a 540 billion parameter model. And they have a companion code model called Palm Coder, which is same size code model. And later, we also found that those models are severely undertrained, and later they improved that and result in Palm 2. So on the side of math language models, in June 2022, Minerva paper is out. So this is a fine-tuned Plum paper for math reasoning, also up to 540B. They show that if you train on scientific papers and train a bunch of math tokens, it's going to improve quantitative reasoning ability by a lot. And towards the end of last year, the first major data work of open source code is released called the Stack. It's a 3 terabyte of permissively licensed code data. And this is really a foundational work for many code language models in the future. And this year, I think many of you, yes. That's a data set.
Can you clarify what you mean by undertrained? Do you mean not having enough data?
Yeah, they don't have enough data, and also they are not trained for enough epochs. Right, any more questions? Good. So entering this year, you probably all know Llama. So this is I think the first language model that is trained with compute optimal in mind. It's trained with much more data, but it's not as large, but much more performant than larger models. And in a month, GPT-4 paper is out, and it is state-of-the-art in every aspect, coding included. Many of the ChatGPT variant I'm using is GPT-4 and still powered by GPT-4. Though we also need to mention that that model is fluid and constantly changing its backend. But in May 2023, StarCoder is released. It's the state-of-the-art in open source, matches the Codex 12B model in performance, and is trained on the stack. And it's also trained with compute optimal in mind. Yeah. Sorry, yeah, compute optimal refers to what described in the Chinchilla paper. Basically, if your model size increases, you also want to proportionally increase the data size, and that would also increase the number of the amount of computing needed to train the model. Yeah, if you train a model with same increasing the model size without increasing the data size, you're going to see diminishing returns, and the model doesn't really scale. So in August, Code Llama is a model that is shortly released after Llama 2. So it's continued training of Llama 2 on code. Though Llama 2 have seen some code in training, Code Llama takes another step towards a more code-specific language model. And also around 2 months ago, Lemma is the first open source math model trained on ProofPile. By continuing training of the Llama. And also Lemma is a model that led by a Yale undergrad that was working with us last year. So yeah, any questions so far? History lessons, all good? Okay. So now let's talk about some methodology. So first, I want to talk about the steps needed before training. So training is definitely an interesting part, but how to create and collect the data, do correct filtering and tokenization is also equally, if not more important. So how do we typically do this for code language models? So first, for data source, as you would imagine, it's mostly GitHub and similar platforms. There are so many code on GitHub that we need some filtering. So one thing that people do is quality filtering, as data quality is obviously very important. So take SantaCoder, which is an earlier, smaller version of a StarCoder, an earlier version, as an example. So the filtering of GitHub stars have to be equal over 5 for choosing repositories. And also there's this interesting concept of comment to code ratio, which also makes sense intuitively. You want a repository to have as much comment as possible, because good documentation, good commentation is a sign of good quality code. But you don't want that to be super large, because if you see a piece of code with more than 80% of them being common, maybe this is just a stub and it's not really used, or maybe just some scratch pad that people use. And also for license, this is important and differs from creating a data set for training natural language model. So only permissive license open source repo may be used. So what's permissive license? So in the licensing world of open source software, there is a concept of copyleft and copyright. There are certain licenses such as GNU license that forbid that has basically, if you use a GNU license software, your software also has to be licensed GNU, hence copyleft. So typical copyright permissive license includes MIT license Apache 2.0. Is still can we use non-permissive license open source repo? I read the license. It's a software. Do we consider AI model software? Is sort of a gray area. That's why people tend not to use non-permissive licensed open source repo. So another important step is deduplication and also decontamination. So deduplication means that we want to remove duplicated files from the training data, because previous work suggested that repeated training data can significantly hurt the performance, and it's also backed up by several other work. Decontamination means that we want to remove the files that contain solutions to benchmarks used for evaluation. So if we have some downstream benchmarks that we want to evaluate how good our training models are, we better not to have solutions of them in our training data. In this way, we can better measure generalization ability of our trained language models, and not be suspecting whether our model just memorizes solution in the training data. So the way to do this is roughly in two categories: exact match and a near deduplication. Exact match is just what it sounds. You match two strings. If they are the same, they're the same. But in many ways, that's not enough, because for code, you can imagine there are two pieces of code that just change in some white spacing, or just changing some indentation, or just changing variable names, but they still function exactly the same. So certain methods can help with this. It's called near deduplication. We can use things like Levenstein distance, min hash, to do this. Basically, you find very similar programs, and also you regard them as the same and prune them from the training data. Here is another interesting and also painful subject called tokenization. So recall from lecture 3, we talked about how we need to tokenize a sentence to subword tokens and embed them and be fed to a transformer model. So tokenization is a very big deal for coding tasks. And let me explain why. So code and format looks very similar, but also very different from natural language. So by similar, the semantic meanings of the variables, of the functions, and the class names works the same in plain English. For example, you can just read those variable or function or class names and guess what this function is doing, because all the words are just English words. But also you may start noticing some differences. For example, the camel case and also the underscore separated variable names, which is not common in natural language. By difference, those things are very annoying and messing up with your tokenizer, but they appear quite a lot in code. such as white space characters, punctuation, and indentations. So here are some examples. Here's a DF dot shape. If you regard this dot as a period, then you're going to have a hard time. And also in the second case, for clarity, I typed all the tabs as \t instead of 4 or 8 or however many you want spaces. And each of the spaces in a typical natural language tokenizer will be a token of its own. So it takes a lot of space just to encode white space tokens. Same thing with indentations. So indentations in some program languages, such as Python, it denotes semantics. If you mess up with indentations, obviously it will not compile. Indentations are basically white space characters, which is easy to be messed up with tokenization. So how to get a good tokenizer for code is basically a trade-off between similarly for natural language models with vocabulary size, number of tokens needed to encode the same sequence, and generalization ability for different tasks. So this is a table from a recent paper studying specifically for tokenizations for code language models. And here you can see different levels of tokenization can be done by making different decisions, whether you want to extend extend a token beyond punctuation or white spaces, or you allow any arbitrary association of arbitrary characters and bytes. For example, if we take level 4, we can encode a whole 4i in range as one token. But in this way, we have a generalization problem because if we do this, if we want to do a code completion, we have 4i and we want the model to complete the rest. It's going to have a hard time doing that because it mostly seeing 4i in range as a whole token. It doesn't see 4i token. If 4i is another token, I haven't seen it quite often to make the association. Yeah. Yeah, that's a good question. So for a lot of the code language models, early code language models, they train their own tokenizer based on code data. Nowadays, people typically mix code data, have some significant portion of code data, like 10, 20%, 5% in their training data. So, and they train their own tokenizer anyways. So those code data is already mixed in. Yeah, tokenization is typically done after you collect the data before the training. Yeah. Before pre-training. Yeah, you typically use the same tokenizer for fine-tuning. You probably sometimes you add a few special tokens during fine-tuning. But yeah, the tokenizer is typically fixed. Sorry. Yeah, so yeah, this is also I think we talked about this in lecture 3. So imagine you only have English and you have only character-based vocabulary. So your vocabulary size is only 26, but every sentence is going to have a very long encoding, right? If you have every English word in the dictionary as your vocabulary size is going to get large, but also your sentence encoding is going to get shorter. Make sense? So who will be the yeah, so from level 0 to level 4, number of tokens decreases. But the generalization ability also decreases because here 4i in range is encoded as a single token. If I want to have a co-completion, if I type the 4i, it is a sort of a special token to it because it mostly seen 4i in range as a whole token. So it's not able to make the association and do the completion. Right. Any other questions about tokenization? Okay. So now let's talk about training. So similar with natural language models, the code language models also can also be categorized into a few categories. First, I'm going to talk about decoder-only models, which are also sometimes called GPT models. So for these type of models, the model architecture and pre-training objectives mostly follows those of general purpose language models. For example, Codex follows GPT-3. Something interesting happens. That happens here is multi-stage training. So some models, code language models, are based off a general purpose language model through continued pre-training. For example, on the CodeGen model, it's first trained on the Pile, which yields the CodeGen natural language version, and then it's trained on the BigQuery, which is a set of program languages and programs and code. And it yields the CodeGen multi version, and then it's further trained on a dedicated Python dataset, which yields the CodeGen mono version. And also in the Kolama paper, they also have a pipeline where the model is taken from Llama 2. And it's trained on code and trained with infilling, which I will explain later. And then is further trained on Python code and add some other post-training steps, which gets us Kolama. So the multi-stage training is mainly to save compute so that you can start your code language model with a strong natural language model and basically boost the ability to write code with it. So code infilling or fill in the middle, I think we also talk about FIM models in this class. So infilling means that you have a prefix, a suffix, and you want to find what's missing in the middle. And this is very useful for many code tasks. So here's an example, which is docstring generation. You have your function header, you have your function body, and now you just want to have a natural language describing what you have done here so that you don't have to write the documentation yourself. So this is a perfect example for infilling. And how infilling is trained is via data augmentation. So basically pre-process the data we have and swap the order a little bit using a special token. Let's call the special token IF in infilling. So previously we have prefix, middle, and suffix. And now we inject the infilling token there. And so also after suffix, and ask the model to complete the middle at the end. So in this way, this is a quite neat trick so that we can use a autoregressive language model and still train it the same way, but the model have some infilling capabilities because in this way, it has access to both the prefix and suffix when it tries to predict the middle. Another category of models is encoder-only models, sometimes also referred to as BERT models. And also you would see the term code representation learning to describe these models. So here is a interesting fact. So code is multi-model, and it's usually automatically it's usually automatic to obtain other modalities. So for code, we typically just think about natural language and its surface form. But in reality, in this world of program languages and software engineering, the code is also parsed into many different formats. For example, you are seeing here AST, abstract syntax tree, and also on the right, CFG, which is control flow graph. So the code can be represented in different ways called different modalities. And the nice thing about that is that the conversion between them is usually automatic process using static analysis tools or compilers. So in addition to those, we also have data flow graphs, which describes how the variables flow into different functions and different scope. There's also dependency graph that defines what's dependency between different variables. If you have A equals B plus C, the A depends on both B and C. And also people try to use compiled machine code, which looks interpret not possible to interpret by us, but people also found that sometimes adding machine code is easier to find certain bugs. So the general idea that many code representation model employ is jointly encode other modalities with the surface form of the code. So here is an example from the graph code BERT paper. Basically, they use a data flow graph in addition to the natural language and the source code, and encode that jointly and attempt to learn a better representation of the code. Surface form just mean the code that we all see, that we all write. Yeah. Say that again. Yeah, so for different models, they have different approaches. So here they use data flow. So you can see they represent for the source code, they represent, is it too small? They represent all the variables as a graph. And then they append, they arrange the variables in this topological order and pass them into as part of the inputs to the encoder model. So here you can see three modalities: text, code, and variable sequence, and they encode them jointly, and they have different objectives that's designed for each part to make sure that the model is learning from different modalities. For example, here variable alignment, and here data flow edge prediction. They're generally encoded at the same sequence, so they're the same. Okay, so another category is encoder decoder models. So the representative models here are BART and T5. So in this class of models, typically a mixture of classification and generation tasks for code are used during pre-training. So in this part, researchers can get very creative in proposing new pre-training tasks. So here is an example with code T5. So code T5 is a model that uses encoder decoder architecture and have multiple tasks during pre-training, including mask spam prediction, mask identifier prediction, identifier tagging, generation, etc. So because it has an encoder and decoder, you can design tasks that only use the encoder or only use the decoder or both. And you can have a mixture of those tasks and design a training loss that take advantage of all these tasks. Yeah. Any questions so far? Yes. Okay, let's go on. So another way to train your code language model is through reinforcement learning. So many of you probably heard, and it's probably taught in this class, ROHF, reinforcement learning from human feedback. different from that, code models or code generation is a natural task to apply reinforcement learning because we can typically automatically obtain feedback from computers. So for example, if we have a parser which parses a piece of code into a syntax tree, if it doesn't parse, it has a syntax error. So we can use a parser to get some very basic level signal. And we can also use compilation from a program language that compiles, whether it pass or fail compilation. Some errors might be caught by compilers. If it doesn't compile, it's a sign that the model is not doing good. If it compiles, we can use runtime error as a way to know if the model is doing a good job, because if it compiles, it runs with some index out of range error, means that it's not thinking carefully enough about the boundaries. And we can also use test cases as a last layer of defense to defend against wrong code. And for some of the work that employs reinforcement learning, sometimes they assign different reward for all kinds of different scenarios. For example, this is a reward function used for code RL, and some other work that use reinforcement learning for training code language models. And yeah, code RL is one example, which uses an offline actor critic network, which I will not delve into. And recently there is also a paper called RLTF, reinforcement learning from task feedback. It's an online RL framework with additional feedback from the compiler, and also textual feedback for more fine-grained reward. So the benefits of using reinforcement learning is that it's not limited to learning from a single solution from the data set. So if we do fully supervised fine-tuning, we typically have a natural language paired with a program, but we all know that for the same natural language specification, we can have different programs that fulfill that. So by using reinforcement learning, it typically employs a combination of sampling and learning, so the model can learn from its own samples, and the samples is typically diversified in a way that the model can learn from different format of programs or different semantic programs that can solve the same problem. It also releases a dependency for annotated solutions. So with reinforcement learning, you only need an input and a way to check the output, whether the output program is correct, for example, test cases, and you don't need a correct gold standard program anymore. And also is able, we are able to directly incorporate preferences. For example, we can say that, okay, we definitely prefer a model that passes a parser and fails at compilation to a model that doesn't even pass a parser. So you can incorporate such preferences already in the reward function. It also have its limitations. First, insufficient test cases can easily lead to false positives. So because we use test cases to detect if output program is right or wrong, if we only have very limited number of test cases, which is a lot of times is true for benchmarks, only passing, for example, 1 or 3 test cases does not say that this program is right. Maybe it's overfit to the test cases. And for example, if you have a program that separates odd and even numbers, and you have and your implementation is have a big switch between the numbers of 1 to 10, and your test case is only 1 to 5. This is obviously a wrong implementation, but you still pass all the test cases, and this is a potential risk. And also another risk is that rewards are typically sparse and underspecified, especially if you have a hard problem, and especially start with a weak model. because the pipeline usually employs a combination of sampling and learning from the successful samples. If you have a complex problem with weak model, you may not get any of those any successful cases at all. Then the model doesn't really learn at all. So this is a typical problem of reinforcement learning. There are ways to mitigate that, but just keep that in mind. Yeah, so basically, if you want to learn from test feedback, let's say we start with a model 0, M0, and then you, given an input, you try to sample a bunch of solutions that hopefully solves the task. If you solve the task, and then say you have certain samples that solves the task, and then you can optimize towards those samples and say, okay, those are the samples I know are correct because the past test cases I want to optimize to increase their probability.
You mean sample from like
sample with the model, with sample using the model to get solution candidates.
So what is sample from?
So basically, if you're this is, if this is your input, this is your output. Input is natural language, output is code, and you have a model that is parameterized by theta, and then you just sample from this model autoregressively. Yeah. Any other questions before we go into post-training methods? All right. Okay, so now that we have trained the model, we are not done to improve the performance of it because there are a whole bunch of ways that we can a bunch of methods that we can use to improve the code language models. So here is a category of my personal favorite, the neurosymbolic approaches. So I'm going to talk about 3 different categories of neurosymbolic approaches, and this is especially exciting for code because code generation using a language model is neural, and code execution using interpreter is symbolic. So it's a very natural application of neurosymbolic approaches. So the first way to do this is incorporating code execution. So we learned that during training time, we can use reinforcement learning and use execution as a signal to provide reward for reinforcement learning algorithms. But also at test time, we can also use execution information to help improve models. So here are some examples. So a very naive way to do this is sampling plus filtering. So this is used in the Codex paper. What we can do is we can sample a bunch of solutions, and then we can filter out those that pass a small that fail to pass a small subset of the test cases. So if you think about the language model with the filtering as a whole automatic system, as a user, you don't really care about what's happening underneath. You only care about whether the top choice that provided to you is correct or not. So you can add some automatic filtering process using execution. And from the results here, we can see that from the last 2 rows, you can see that the filtered performance is much better than the raw performance. And let me quickly explain what PASA-K is. PASA-K means that if you sample K times from the models, or if you provide K candidates from the models, if any of them passes all test cases, if so, PASA-K is 1. If not, it's 0, and it's averaged over all the examples or the tasks over the data set. Another category is sampling plus filtering plus clustering. This is what is used in AlphaCode. So in the AlphaCode paper, what is done, what they do is they sample lots of diversified program candidates, up to 1 million candidates, and you can use use the open test cases to filter out many of those solutions that doesn't pass the open test cases. So the difference between open and closed test cases is if you have done for example, online programming websites, you know that there are some open test cases where you can test yourself, and there is some hidden test cases that only gets executed when you are submitting it. And here, they're only using the open test cases and filter out those that doesn't even pass that. And in addition to those steps, they diversify the picked candidates by clustering and select from different clusters. So what this means is that imagine you sample 1 million code candidates, and now you do correctness filtering. You've probably filtered out half of them. You're left with 500,000 program candidates. And now you're wondering, I'm only allowed to submit 10 times. How am I going to select 10 from those massive number of program candidates? So what they do here is they can do is clustering. We can cluster all of those samples and make sure that we have a diversified enough set of submissions to the competition that they come from different clusters. For example, maybe this cluster of programs is solving this task with dynamic programming. Maybe we want a candidate from that, and maybe we'll want some candidates from other approaches. So by a combination of these methods, they have pretty good performance. They reached average performance of human programmers in code competition tasks that involve around 5,000 human programmers.
This kind of thing, trade-off is
Yeah. Yeah, it's a huge trade-off. But this trade-off is also a parallelizable trade-off. So what I mean by that is if you have a pipeline-based system, such as sampling plus filtering plus clustering, each step is strictly dependent on the completion of the last step. So your total latency is inevitably increased. But if you have a parallelizable cost, which is something like sampling, you can imagine that I use one machine to sample 10 examples. I can use 100,000 machines to sample 1 million examples. They will be the same time. So this is also a parallelizable cost. Yeah. So yeah, and you can see from the results that this scales pretty nicely given different sampling budgets. Another way to do this to incorporate code execution is through sampling. So we can do sampling plus verification plus voting. So how do we do this is we can train another model to verify the programs with its own execution results. So in this work, we can aggregate, in addition to the verifier, we can also aggregate the probability from the programs that reach the same execution results. So this is related to the problem we talked about before, which is if you have a natural language, you can have multiple different programs that gets a correct answer. And if for some tasks, for example, text to SQL queries, we only want the final answer, then we can essentially vote on the final execution results. And in this work, we also use execution results as part of the input to the verifier. And the verifier basically verifies whether a program gets the correct execution result that we want. Yeah. Yeah, that's a good question. So those methods are mostly used at test time, which means that the model is already there. They're using this method to boost, get a final mile to the performance. But in principle, you can use the same method in combination or with the sampling we talked about. You can use the same method in reinforcement learning and try to get more diversified samples, and the model can learn from by itself.
You know, like these pipelines used to get an accurate explanation of the laws, and then make it
What I meant is that so the sampling plus filtering is typically what's used in reinforcement learning as well, because you want to sample from the model and then learn from the correct samples. The clustering method may also be used in that process if you want to diversify your programs that you want to learn from. For verification and voting, I don't see a direct application, but maybe there is a way to.
So they're used for getting like with that also.
Say that again.
So these pipelines are used to get a good estimate of how well the model can do.
It's in training time, maybe. Here I'm mostly talking about at test time. So at test time is mostly about how to use a trained fixed existing model and get better performance using several tricks. So here we don't alter the parameters of the model itself, but basically by sampling, we have a probability of all the program candidates, right? But maybe that's not the best, right? This is the probability that model think should be a distribution, probability distribution that model think should be among those program candidates, but maybe we have better information available, for example, execution information, and that should be taken into consideration. Yeah. So another way to combine neural and symbolic approaches is constraint decoding. So maybe some of you by this point have this question. We had code completion for a long time, right? Long before like large language models, you have those tools in your IDE that pops out. Like this, if you do import numpy as NP and you do NP dot and a bunch of options just pop out. This looks like a language model, right? And how is this done? So programs are informal languages, which means that they are regulated by strict grammar. That means at any point of writing a program, the selection of valid next tokens is quite limited. For example, here, if you do NP dot, the tokens next after that can only be methods or variables that exist in the NumPy package. So before language models, how we do completion is by a completion engine. So basically, this engine tells you the valid next tokens with static analysis, though the token here and the token we have for language models are slightly different. So take this picture as an example. If you do NP dot, because the completion engine knows which Python environment you are at, it knows which NumPy version and all the libraries installed in your current environment. It can quickly retrieve all of those valid tokens and valid methods and classes and variables that are available and use a list for your selection. So as we said, this sounds a lot like a language model, right? But this is also a symbolic process, which means that it runs on CPUs, it's deterministic, it doesn't need any training, and is adaptive to your current environment. So maybe some of you have the experience of you want to implement some functionality using NumPy, and then ChatGPT gives you a solution that is using the early version of the NumPy and have some deprecated functions that does not exist. And with completion engines, you don't have that problem because it's always akin to your own environment. So people have tried to combine language models with completion engine. So you can imagine that for the next token, what language model gives you is a distribution over all the possible tokens in the vocabulary. And what completion engine gives you is a 0-1 selection of all possible tokens in its own vocabulary. And it is possible to combine them and filter out the next token from language models that are not approved by the completion engine. Sorry. So yeah, this way you get the best of both worlds. So another way to combine symbolic system is through planning and search. So here's another property of programs. They are compositional by design. So for human programmers, we typically decompose the problems into smaller parts and write functions to solve each of them. So this involves planning and implementation. And then given the components, we can use a solver, which is symbolic, to find out if they are sufficient in completing tasks, which resembles search. So this is more like completing a jigsaw puzzle. So you already have the pieces, and now you're trying to figure out how to combine them to have to complete the blueprint that you have. So one example of this is the parcel paper. So what this paper does is it decomposes the problem into several sub descriptions in natural language, and then it employs a model to implement those functions, and another symbolic solver. After we implement all those functions, we use another symbolic solver to find a composition of those functions that will complete the final task. Any questions? Yeah, if you don't know what a solver is, it's a you probably know what an equation solver is, right? You define some variables in equations and use a solver to find out what the value of the variables are. And you can also, for example, if you have a Sudoku problem, it's a constraint problem, it's a constraint satisfaction problem. And you can also use a solver to solve that. For programs, it's the same. If you have some specification that you want to satisfy, and you have certain components that you can compose, you can also use a solver to find out, to utilize the constraints of each functions. For example, its function signature. For example, if function 1 takes a string and outputs a integer, function 2 takes 2 strings and output a string, function 3 takes an integer and output a string. Those are constraints that you can use to restrict your search space for the solver until it finds a solution that passes all the test cases. Another example of this is a recent work called set LM. So it employs a deductive reasoning process, which is different from the chain of thought methods that we'll talk about in this class. So basically, for a problem in this example, it's a math problem. You simply defines what it says. You simply declares what it says in the natural language, and then you use a solver to solve the result. So this is in contrast with chain of thought reasoning, where you have to reason deductively and use an interpreter to get the result by execution. So in addition to neurosymbolic methods, there are also prompting methods designed specifically for code. So we talked about chain of thought prompting, which explicitly writes reasoning process as natural language steps. There is also a method called program of thought prompting, and also similarly a method called program-aided language model. So, and these two methods, they explicitly write the reasoning process as a program instead of natural language, and use program execution to obtain the final answer. So the benefit of using the program execution to get a final answer is that it avoids awkward and complex numerical reasoning and symbolic reasoning steps. For example, doing division is quite hard for large language models. But it's trivial for programs. So using programs as a reasoning process basically decouples the need to represent the problem and also the solution to obtain the solution of the problem. So this works well with math and other symbolic reasoning tasks, which are the main benchmarks of those two papers. This is also closely related to the tool use of large language models, as we talked about in previous lectures of this class. Another category that works quite well for code is retrieval augmented generation. So we talked about RAGs in this class. For a quick recap, retrieval augmented generation retrieves relevant pieces of information from some knowledge base and include them in the prompt. So again, as an analogy to human programmers, when we code, we look at a bunch of different things. Obviously, we'll look at the current file. This is also what a language model does. We know what the defined variables, function, the classes are, but also we look at a whole bunch of other things. For example, documentation of external libraries. We also look at definitions of imported functions and classes. We also search over the web for GitHub, Stack Overflow, and other coding tutorial websites. And if we have access to those information when we code, we should give those information to large language models as well, right? So there are papers that try to incorporate those ideas for large language models. So dot prompting is a method that retrieves documentation of the external libraries and put them in the prompt so that model knows how to call this function and some example code snippets. Also, people have tried to append the definition of the functions and the classes that are imported. For example, in this paper at SML this year, they propose a repo level prompt generator that retrieves some of the important functions and classes and put them in the prompt so the model knows what the function signature is like when they call the functions or initiate the classes, initialize the classes. And more earlier, there is a paper called Ratcoder, which uses retrieval augmented generation for code generation and summarization, and retrieve similar programs with similar specifications from a set of programs that helps the generation of the current task for code generation or code summarization. So in summary, here today we first have a brief history lesson about code and math language models. We talk about several techniques during data collection, and we learned that tokenization is easily done wrong, and it's important for model performance, and it needs to be taken care of carefully. We learned about several different architectures of code language models. We learned code infilling. We saw several reinforcement learning methods for code language models. We also talk about several post-training methods, including neurosymbolic approaches, prompting methods, virtual augmented generation for code. So there are some more topics I hope to cover. When I was prepared for the lecture yesterday and a couple of days before, I found out that I really need a couple of more lectures to cover a lot of the topics I want to cover. So for example, code language models is used in many interdisciplinary applications. The first example is using code language models for robotics. You can generate code as a policy and use the success of the manipulation of the robot as a learning signal, and do back propagation on that and train a model that generates code to control robotic arms. And you can also use this for program language field. And recently there's a paper on large language models for compiler optimization, which is a very important topic in program languages and formal methods. There are also a large amount of work involves self-improvement. With code, you can also do this by bootstrapping, by generating your own test cases, or even debug by the model itself. And also there are more ways to learn a code language model than the ways we talked about before. For example, the Scratchpad paper shows that you can use intermediate debug information for the programs and incorporate them in training, and the model learns to reason over programming steps. And also in this last paper, we showed that you can learn math reasoning from some self-sampled correct and also partial correct solutions. And here we define partial correct solutions using partial correctness, and you can learn from programs that are not completely correct, and you can also learn something useful from them. And we show that this also improves performance. So yeah, this will be my last slide. Hope you enjoyed the lecture. And any questions? Yeah.
Like you use the method, take the correct or like the good next program to input the generation, or like I don't get a problem.
So okay, so this is a test time method, so which means that the model is already there, right? What it does is that you sample a bunch of candidates, and then you basically give them a re-ranking, right? Because new information is available, such as execution information. So maybe I should rank some of the programs first. For example, those that doesn't compile, I should probably not output those, right? So instead of using beam search to output 5 most probable programs, I should sample 100 programs and use other information to filter out those, because what the model think is most probable might not be most correct.
That's
Yeah, that's an inference time shrink. Yes. Yeah.
So there's any research to like adapting a model to like updates to documentation, like relatively minor changes, but like you have to, use different syntax, the logic is the same, that sort of stuff. Is there like a low cost way to do that?
So you're talking about maybe online learning of a large language model, like if I'm understanding correctly, if for example a library is updated, right? So I want now the whole training data, the model is trained on the old data, which means that it's receiving outdated information, and we don't want to train the model all over again. Yeah. So there are research on this, but this is also very hard. What people typically do is just do retrieval augmented generation. You retrieve those documentation, you tell the model, forget what you learned during your pre-training. This is an updated documentation. You should refer to those. This also applies to domains like news, right? If I ask ChatGPT about something happened yesterday, it doesn't know because it doesn't train on that. But with retrieval augmented generation, and also sometimes with tool use, for example, if we use a web browser or Google search as a tool, then I can know what happened last time. Yes, yesterday. Yeah. Yeah.
Very nice talk. Thank you for that. And I have a kind of a general question. So, like, I think most of the thing you mentioned is kind of driven by the industry, right? So I was just wondering, what is your perspective about like people in an institution can do kind of a differently, since we're kind of limited on digital purpose and all that.
Yeah, that's a very good question. So one other thing I did not have time to cover is some products that is already out there. In addition to GitHub Copilot, so Google have this model called Didact, DIDACT. So basically, it's a multitask model that does everything a programmer does. In addition to code generation, it generates your commit message. It fixed your code based on the test case outputs. It's fixed your code based on the code suggestions by your code reviewer. It does a whole bunch of things. So back to your question. Yes, a lot of this is driven by industry, so as a lot of progress in large language models in general. But in large language model for code, industry have an extra layer of incentive, which is help their own developers and software engineers internally. So as far as I know, most major tech companies have their own code language models served internally, and they can train on all of their internal code, which are probably more in domain and have higher quality and in the certain style that they want to write code in. So this is has a huge economical effect in saving costs for the companies. That's why a lot of the companies are already in this. For academia, I think exploring post-training methods is still interesting. And also I'm specifically interested in the combination between narrow approaches and symbolic approaches, because there are 30, 50 years of development of program languages and software engineering domain that produces a massive amount of tools and very nice tools. For example, compiler optimizers, compilers itself, and also many static analysis tools that are not typically in the mind of say an LP or machine learning researcher. And as far as I know, many of those commercial software or products, they already did this pretty well. 1 second. Any more questions from anyone? Because I think we're running out of time. So yeah, if you have, yeah, feel free to leave if you have.
But why do you then why the
Say that again. one second, let me stop